Section 2.3, Other Set Operations and Their Properties. We're mostly going to focus on Venn diagrams and how to write out the different operations that we can apply to sets and how they're represented in Venn diagrams. But as you read through the textbook, you'll learn more about the relationships between set operations and logic, and then the properties of these sets and logic operations. We're going to start this as a case study. So we're going to tell a story about 10 best friends: Alex, Blair, Casey, Drew, Aaron, Francis, Glenn, Hunter, Ira, Jade. They're all best friends. And if it's not popping out at you, notice that everybody's first letter of their name, it's alphabetical. So A, B, C, D, E, F, G, H, I, J. That was intentional. So we have these 10 best friends. And we know that Alex, Casey, Drew, and Hunter, they like to play soccer. And if we wanted to represent them in a set that contains everyone who likes to play soccer, then we could draw a circle, label it S for soccer, and place all 4 of these friends in that circle. But if we happen to find out that Casey, Drew, and Jade play tennis, then maybe we want to represent the group of friends who like to play tennis. So we'll draw a circle, label it T for tennis, and we'll place Casey, Drew, and Jade in there. Now looking at these 2 circles, the way that we have them drawn, they look disjoint. Disjoint means that they don't overlap. However, we can see that there are 2 people, Casey and Drew, that appear in both circles. So rather than give the illusion that these sets are disjoint, we want to represent that they are overlapping, that they contain some of the same people. So instead of drawing 2 separate circles, we'll draw 2 overlapping circles. And then we'll write Casey and Drew in that intersection, the overlapping portion. Now their names were a little bit too long to spell out in that tiny little space, so I'm going to represent Casey with a C and Drew with a D. Notice that Alex and Hunter are not in that overlap because Alex and Hunter don't play tennis. And Jade is not in the overlap because Jade does not play soccer. If we were to still just look at each circle individually, within the soccer circle, I still have Alex, Casey, Drew, and Hunter. And if I looked at just the tennis circle, I still have Casey, Drew, and Jade. So I can use these diagrams to help sort things out and to see anything that's being overlapped. One of the first operations we'll talk about is a union. A union is when we say anybody who plays soccer or tennis. So we talked about conjunctions and disjunctions in the first section of this book, chapter, and we said and or represented a logic operation. Well, it's doing that here too, but we have a visual to help us understand. If I'm talking about all the friends who play soccer or tennis, then I'm talking about Alex, Casey, Drew, I forgot what H was, whoever H is, and J. So I'm talking about all 5 of the people that appear in the diagram. The union often represents the word or. That includes everything that's in both circles. And an intersection is kind of the opposite of a union. The intersection of these 2 sets represents all the friends who play both soccer and tennis. So Alex does not play tennis, therefore Alex would not be in the intersection. Casey and Drew play both soccer and tennis, so Casey and Drew are in the intersection. So intersections are often represented with the word and. So let's take a moment to appreciate the differences and then the notations. Unions come with the word or, and we use a little U between the set S and T to say that we have unioned them. And then we list out all the elements that belong in the union. With the intersection, that's represented with the word and, we use kind of an upside down U, almost like an A, between the two sets, and we list the two friends that belong in the intersection. Now this is slightly different than when we looked at the logic statements. Remember, if we had OR with P or Q, we used a V. And if we used AND with P and Q, we used kind of a caret. So similar, but a little bit different because P and Q were statements, S and T are sets. So the notation's slightly different to draw attention to the fact that we're looking at a list of elements here, not a true or false statement. The next operation we'll look at is set difference. If we're looking at the sets S and T, and we do the set difference, S minus T, that's basically talking about any friend who plays soccer but does not play tennis. So we would fill in or consider anybody that's in the S circle but outside of the T circle. So we need to ignore the overlap there. Or vice versa, we could have said any friend who plays tennis but not soccer. In that case, we'd look at anybody who's in the tennis circle, but not in the soccer circle. So outside of the soccer circle, that's only Jade. So of our 10 best friends, we know that Alex, Casey, Drew, Hunter, that's who H was, they all play soccer. Casey, Drew, and Jade play tennis. And now we're learning that Drew, Glenn, and Jade, they play volleyball. So I have my soccer circle, I have my tennis circle, and now I want to draw a V circle for volleyball. It's going to include Drew, Glenn, and Jade. Now, Drew is already in the diagram, Glenn is not, but Jade is also in the diagram. So when I draw my volleyball circle, I need to make sure to include Drew and Jade inside of that circle. So I draw the volleyball circle to overlap both the intersection of S and T and the portion of T that contains Jade. So I have Drew, Jade, and Glenn inside of the volleyball circle. Now we have 10 best friends, but not all 10 of them like to play sports. So if we wanted to represent the entire group of 10 best friends, we need to draw a rectangle around our three circles to represent the entire universe, which contains all 10 best friends. So of the friends who don't play sports, we have Blair, Aaron, Francis, and Ira. They are part of the group of 10 best friends, but they don't belong to any one of these three sports circles. Now, I said they don't play sports. Maybe they do play sports, but the sports aren't soccer, tennis, or volleyball. Maybe somebody plays baseball, maybe somebody does track and field, who knows? But here we've used a diagram to help sort everybody out so that we can easily answer questions. For example, does any of the 10 best friends like to play soccer, tennis, and volleyball? Yeah, that would be Drew, because he belongs to all three of the circles. Or do any of the 10 best friends not like to play volleyball? Right? If you're going to host a party and invite all of your friends over, which sport would you want to play? Volleyball? Probably not, because there's Blair, Aaron, Francis, Ira, Alex, Hunter, and Casey. They don't play volleyball. That's a lot of your friends who would be sitting on the sidelines while you're trying to have a volleyball party. So I would say probably soccer would be the game to do because that has the most people in it. But anyways, we've used a Venn diagram here to sort people into different categories. That way we can answer questions quickly about what people belong to each category. Some other operations we'll look at is that the union can happen between more than just two sets. So if I wanted to talk about the union of all three sets, how many of the friends like to play soccer or tennis or volleyball, I would shade everything inside of all three circles. So or says to shade everything in all of the circles. If I just wanted to talk about the set S, I could. I would just ignore anything that's not inside of the circle S. So even though I have all of these circles overlapping each other, I can narrow my focus in just to look at one set S. I can still union just two of the circles, even though there's three circles here. Maybe I want to talk about the friends that like to play tennis and volleyball. Well, we can still do that. We can look at the intersection of any two sets. So between soccer and volleyball, Drew is the only one that likes to play both of those sports. I can combine different operations. So here I'm looking at the intersection of soccer and volleyball, which we said was Drew, but then I'm going to remove tennis. And we can see here that there's nobody in that section. So the whole intersection of soccer and volleyball did include Drew, but when I said, okay, don't include anybody who likes tennis, then I'm this empty space over here. So we would say that's the empty set. We could write that with two curly brackets, nothing between them, or we could use that 0 with a slash through it to say the empty set. I can talk about the universal set. That's everything inside of the circles, outside of the circles. That counts up all 10 friends. I could look at the universe minus a set. So this would be of the 10 friends, everybody who does not play soccer. We call this the complement of the set S, and we can write that as S with a superscript C, almost like in place of where an exponent would be. Or we can write that as S with an overbar to say S complement. They both represent the same thing. So we know what a union is. That's represented between two sets with a U. That's the OR operation. We know what the intersection is. That's represented between two sets as like the upside down U. That's the stuff that's in both sets. The subtraction symbol is set difference. The little superscript C, or the overbar, means complement. We've talked about the empty set as well as the universal set. Let's do some examples here to help get familiar with set unions, intersections, difference, etc. So we're given two sets, A and B, and we want the union. Maybe we draw a diagram to help us. And it's a good idea not to start your diagram off assuming that they're separate. Instead, start with two very large circles that overlap and fill things in as you see them. So in the set A, I have 1, 2, 3, 4. In the set B, I have 3, 4, 5, 6. Well, 3 and 4 are also in the set A, so let's move those to the intersection. And then 5 and 6 are in the set B. Now remember, for the union, it's everything that's in both circles. So A union B, that would be 1, 2, 3, 4, 5, and 6. Now you're probably thinking it's not necessary to draw these circles. I could figure that out just by looking at these set lists. But remember, we're trying to develop the way that we explain things. So maybe somebody looks at these two lists and they get overwhelmed looking at all of the numbers that way. An easy way to help make it simpler or to make it more clear would be to sort the numbers into a diagram first, and then you could answer questions about it. All right, we have another set of A and B that we want to sort and union. This time A has the numbers 0, 2, 4, 6, 8, 10, etc. It's all the even numbers. This is an infinite list, I can tell because of the ellipses at the end. And then the set B has the odd numbers, 1, 3, 5, 7, 9, 11, etc. Now it's true that there are no even numbers that are also odd, So the intersection between A and B would be empty. But the union is going to include everything in both circles. So A union B, that's going to take all of the even numbers and combine them with the odd numbers. So our union would actually be the whole numbers. We have two more sets to try here. Set A has the even numbers. Set B has all of the positive counting numbers. So let's do set A, 2, 4, 6, 8, 10, 12, etc. Set B has 1, 2. I'm going to take the 2 from A and put it into the intersection. 3, 4, 5, 6, 7, 8. Notice that the set B has all the numbers in it. The set A, which had all of the even numbers in it, is completely fit inside of the set B. In fact, we could have drawn this diagram to look like this, B, and then circled all of the even numbers inside of B and labeled that A. In this case, A is a proper subset of B. When I union these together, A has elements that already appear in B. So really, I'm just listing off B again. So rather than listing it out, maybe we say A union B is simply the set B, since we already know what B looks like. So that was an example of set unions. Now let's work with some set intersections. We can draw our circles again. I'm going to sort through these one more time, but a little more quickly. So between set A and set B, I can see that there's a couple numbers in common. The number 4 shows up in both, and so does the number 3. So I know 3 and 4 will be inside of here. The intersection is that overlapping region, so A intersect B includes the elements 3 and 4. For our next set of numbers, looking through, I can see that they don't have anything in common. Remember, A had all of the even numbers, B had all of the odd numbers, and there was nothing in between. So then this intersection is the empty set. There's nothing that belongs to the overlap for this two sets. All right, one more. Here we have all of the even numbers, and then we had all of the counting numbers. And we said this one, actually, we can put all of the even numbers here, all of the odd numbers here, so that the set B contains all of the counting numbers. So for the intersection, the numbers that A and B have in common are all of the even numbers, which happens to be the set A. So we could say the intersection here is the entire set A, and that's because A is a proper subset. So remember that we could draw A like this for this picture. A is completely contained within B. Let's practice some set difference. If we have the sets A contains D, E, F, B contains A, B, C, D, E, F, and C contains A, B, C. So let's draw our diagram. We'll have 3 circles, 1 for each set. So we'll label them A, B, C. In the set A, I have D, E, F. I'll write those here for now, but I might have to move them into these intersection spaces. The set B has A, B, C, D, E, F. Well, notice D, E, F, we already have those in A. We have to move those into the overlap. Then B will have A, B, C. But then the set C has A, B, C. So A, B, C would actually need to be in the intersection from B and C. So let's double check that we have that. The set A has all the elements D, E, F. The set B has A, B, C, D, E, F. And the set C has A, B, C. It feels strange to have so many empty spaces in here, but it is exactly what these sets are telling us, that A and B have some overlap, and B and C have some overlap. But A and C do not. Notice that the elements in C are very different than the elements in A. So let's find our set difference. We want everything that's in the circle A but is not in the circle B. So that would look like this space. And that's empty. So that would be the empty set. Whoops. B minus A, that would be everything in the circle B that is not in the circle A. This time that's not empty because that contains anything in the intersection from B and C. So the elements A, B, and C are in the circle B, but not in the circle A. Then B without C, that's everything inside of the circle B, but not in the circle C. So that would be all of this stuff, which includes D, E, and F. And we have one more, and that's C without B. So everything in the circle C, but not including anything that's in the circle B. So that would be this space, and that's empty. And now we might want to take a second to look back at the answers we got for the second and third set difference problems. A, B, C, that's actually the set C. So we could write that B minus A is the set C. And B minus C, that includes D, E, F, that's the set A. So we could write that this is equal to the set A. Now the real power of Venn diagrams is that they can help us sort through lists of data to answer questions that are useful. For example, this problem talks about a survey of 110 college freshmen, and basically they just ask, are you taking physics? Are you taking biology? Are you taking mathematics? Are you taking physics and mathematics, biology and mathematics, physics and biology, or all three? So sometimes when you collect data, you actually ask a question in multiple ways. And the reason why people who write these surveys do that is to make sure that they're getting accurate information. So if somebody said, yes, I'm taking physics, but no, I'm not taking physics and mathematics, you might wonder what's going on here. So what we're going to do is draw a Venn diagram that represents all of the data that we have, and then we're going to use that to answer the three questions below. So I can see there's a few categories: physics, biology, and mathematics. So let's start by drawing three circles: physics, biology, mathematics. And notice that I'm just assuming that they might overlap. We don't know, but it's better to have the possibility than to have to redraw your diagram because you didn't consider it. So I need all three circles to overlap. All right, 25 took physics. If I put a 25 right here, I don't know if any of those 25 also took biology and mathematics, or also just took mathematics. So it's hard to start with that first number. It's not really specific enough. In fact, if we look at any of these first three numbers, they're too general. So instead, we're going to read through and find the most specific information we can find, which is this last bit, which says 5 students took all 3 subjects. So I know a 5 has to go in that intersection of all 3 subjects. Once we've used that, we can cross it off. Next, we can say 6 took physics and biology. Physics and biology, that's this overlapping region right here. I already have 5 in that region because 5 people took physics, biology, and mathematics. And if I want to say that 6 people are in this entire region, then only 1 more can go out here, so that I have a total of 6 in that intersection between physics and biology. And then once we've used that, we can cross it off. Now we know 8 took biology and mathematics. So biology and mathematics, that's this entire intersection. There's already 5 people in there. That means there can only be 3 in this last piece. And if you're wondering, how did I find the 3? Well, if 6 are supposed to be in that intersection, and I know that there's 5 already in there, 8 are supposed to be in that intersection. I know there's 5 already in there. That would leave 3 left. So I'm just doing a subtraction there. And I can double check. If I look at the entire intersection of math and biology, do I have a total of 8 students in here? I sure do, which makes me feel like we did it right. Next, 10 took physics and mathematics. Physics and mathematics is this entire overlap. But there's already 5 people in that overlap, so there must be 10 minus 5 in this other region. And I double check, inside of the overlap between physics and mathematics, do I have 10 students? We sure do. Okay, now we're ready to look at the more specific information. In the mathematics circle, we need to have 48. So far we have 5, 5, and 3. We have 13 in the mathematics circle already. So if I put 48 right here, then I would be double counting everybody in the intersection. So instead, maybe I put like X right here, and then I say 5 plus 5 plus 3, the students that we already count in the math circle, plus X, the number of students that we don't know, that has to add up to be 48. So then we have 13 plus some unknown number X equals 48. And you can either do this by guess and check, or you could subtract 13 from both sides to find that there are 35 left that take mathematics but not physics and not biology. Okay, and we need to look at the biology circle next. We know that there should be 45 students inside of the biology circle. So I'm going to use the numbers that are already showing up, 1, 5, 3, plus the X we're looking for, that needs to equal 45. So we add our numbers together, we get 9 plus X equals 45. Subtract 9 from both sides so that we see X has to equal. Well, we can count up from 9. 9 plus 1 is 10, so we have 1. And then from 10 to 40, that's another 30, so that's 31 so far. And then to 45, we need another 5, so that would be 36. So there are 36 students that take biology but do not take physics and do not take mathematics. Then we have one fact left, which is 25 students took physics. So we'll repeat the process, put a placeholder for the number that we're looking for. We know 25 needs to equal X plus 5 plus 5 plus 1. That ends up saying 25 is equal to X plus 11. Subtract 11 from both sides. We get 14. So there are 14 students who take physics but do not take biology or mathematics. Now, something that I always see students overlook when filling out their Venn diagrams is that it's possible that of the 110 students that were surveyed, some students don't take physics, they don't take biology, and they don't take mathematics. So we need to check and see if there's anybody not represented inside of our circles. The simplest way to do that is add up everybody that is appearing in these circles and then find out if it matches 110. So we'll do 14 plus 1 plus 5 plus 5 plus 36 plus 3 plus 35. Notice that I'm not adding up 25, 45, and 48. 25 is everybody inside of this first circle. 45 is everybody inside of this biology circle. If I added 25 and 45, I'd count this student and these 5 students twice. So we need to be careful of that. So I know 14, 1, 5, and 5, that comes out to be 25. 36 and 3, that comes out to be 39. 25 plus 35, that's 60. Plus 39, that's 99. We only have 99 students represented in these 3 circles, but we surveyed 110 of them. So that means that there's some students that are not represented in the diagram. So it's a little bit off. We would need 11 students. So there will be 11 students in the universe that are outside of the 3 circles we've drawn. So the 110 college freshmen, there are 11 outside of the 3 subjects. So now we're ready to answer some of these questions. How many students took biology but neither physics nor mathematics? So we're going to come to our diagram, and we have biology, the full circle of biology here, but notice that some of those students are taking physics and they are taking mathematics. So we're going to look at biology without including anything in the physics or mathematics circle. So that would be 36 students. And then we might ask, how many took physics, biology, or mathematics? Now that is the union of physics, biology, or mathematics. So that includes all of these numbers. We just added those up actually and found that that was 99. And then one more question here, how many did not take any of these 3 subjects? Well, we found that to be 11. Another thing we want to talk about in this section is something called the Cartesian product. When you have 2 sets, you can make a product of the 2 sets by pairing up elements. This is similar to what we did with one-to-one correspondence, except for it's different because I can cross 2 sets with different numbers of elements. So it's not the same thing as one-to-one correspondence, although it looks similar. Let's suppose a person has 3 pairs of pants that they can choose from in their wardrobe. One pair of pants is blue, another pair of pants is green, another pair of pants is white. Flashy. And they also have some shirts to choose from. They have 2 shirts that they know go with any of those pants. They have a blue shirt and they have a red shirt. According to the fundamental counting principle, there are 6 ways for us to pair these elements up. And to see that, we can draw it out in a table where we put all of the elements from one set on a vertical axis and all of the elements in another set on a horizontal axis. And it's not important necessarily which one goes on the vertical, which one goes on the horizontal. But what is important is that if we are crossing, for example, P with S, if we want the Cartesian product of P with S, then the elements that came out of P need to show up first in the ordered pairs that we're generating. If instead it were S crossed with P, then all of the elements from S would need to show up first. So we would reverse the order in each one of these ordered pairs. So you can kind of make this into a table where you have different columns that represent each of the elements from the set P, and then 2 different rows where each row represents the elements from the set S. And then we order the pair using anything from the set P first. So in this column, blue is the first element of our ordered pairs. And then on the top here, since we're in the red row, red is the second element, And in the bottom here, we're in the blue row, so blue is the second element. It's really important that we keep those orders straight because the first element tells me what kind of pants to wear. The second element tells me what kind of shirt to wear. So if I don't have a red pair of pants, but you wrote something like red, blue, I'll be at a loss. I do have a blue shirt, so that part's fine, but I don't have red pants, so putting red first would be incorrect. Let's practice making some of our cross products or this Cartesian products. If I have the sets A with B, then I can list all of the elements A on the bottom, all of the elements from the set B on the side, and then I can make the ordered pairs. So remember that the letters are going to show up first because we're crossing A first. So we would have A, comma 3. We would have A, comma 2, A, comma 1. And then we need to do the same thing for the B column. B3, B2, B1. And then for C, C comes first, C3, C2, C1. And if we listed it off as A cross B, then all of these elements would be listed. So I can quickly kind of convert this into a list of elements just by putting commas between everybody. And then putting curly brackets at the beginning and the end and saying A cross B is equal to all of those ordered pairs. B cross A is going to have almost the same ordered pairs, but the numbers will come first. So we'll have 3A, 2A, 1A, and then we'll have all of the B's. So we'll have 3B, 2B, 1B, and then the C's, 3C, 2C, and 1C. And then lastly, we want to consider what happens if you cross a set with itself. So we're going to draw another diagram for that one. This will have B, C, and then again on the vertical we will have A, B, C. And then we'll list out our elements. So this would come first from the A column. We would have A, C, A, B, A, A. And then from the B column, that would look like B, C, B, B, and B, A. And then from the C column, we'll have C, 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 B, and then C, A. And it is really important to keep the orders correct because if you accidentally swapped them, for example, if we wrote AC down here instead of CA, we already have AC. And if we make that mistake down here, we're forgetting about the possibility of C, comma A. So it's really important to stick with the pattern that we're using to make this cross product. And once we have all of those ordered pairs listed out, we'll just separate them with some commas and slap some curly brackets on there to say A cross A is equal to all 6 of these ordered pairs.